Oh, we can hear you. Yeah.
Okay.
Thanks again for accepting the invitation.
Well, it's a pleasure. I'm glad to be here and to kick off this great sequence of seminars.
Thank you. Our pleasure.
Thank you. So maybe let's start.
2 minutes. It's 2:58. So we start sharply at 3.
Well, maybe I should see if I can share the screen.
Yes,
definitely.
That'd be the first step here.
Yeah.
Are you seeing my screen?
Yeah.
Yes.
Oh, great. Okay, fantastic. All right, well, just tell me when you want me to start.
Yeah, we will first maybe introduce the tentative plan of the format of the seminar, and then introduce you, and then we will start.
Yes. Okay. Great.
Yeah. How are you? How is the situation in Ann Arbor?
It's still lockdown, so we we can't go out. It's you know, a little bit difficult to get groceries and the standard things, simply because there's a run on certain items, meat, and toilet paper and things like that. So you have to really strategize.
Yeah.
Yeah.
Same here. Yeah.
But otherwise, it's fine. I'm enjoying the relative calm.
Yeah, but for me, I'm practically a full-time father now, so I cannot do much research.
It's not calm at all for you. I can understand. Yes.
Yeah. Yeah. So maybe we can get started.
Yep. Sounds good.
Yeah. Okay.
Yeah.
So hello everyone, welcome to the first session of the online seminar on mathematical foundations of data science. Our goal of this seminar is to make it a weekly seminar on random topics related to machine learning, statistics, and optimization. Currently, we have a huge crowd of almost 2,000 people registered. We are extremely excited about that. Thank you all very much for your participation. Hope you will find this seminar interesting. Also, I would like to thank our fantastic speakers who make their precious time to deliver the wonderful talks for this seminar, especially during such a challenging time due to COVID-19. So before going to the talk, let me first introduce the tentative format of this seminar. We will see how it works and perhaps adjust it in the future sessions according to the feedbacks. The talk will be about 15 minutes long, followed by a small Q&A section. To make it go smoothly, we tend not to interrupt the speaker, and would have questions for the speaker at the end of the talk. So if you guys have questions to the speaker, you are more than welcome to post them using the Q&A function in Zoom, or make comments using the comment function on Facebook. I will collect these questions and ask after the talk. We aim to finish the whole seminar within one hour. So due to the time constraint, perhaps we might not be able to ask all the questions, but we will try our best to address as many questions as possible. And thank you for your understanding. So in today's talk, we are very honored to have Professor Alfred Hero as our speaker. I would like to thank Professor Hero again for accepting our invitation. So Professor Hero is a John H. Holland Distinguished University Professor at the Electrical Engineering and Computer Science, and the R. Jamison and Betty Williams Professor of the Engineering at the University of Michigan, Ann Arbor. He is also the co-director of the university's Michigan Institute for Data Science, and his primary appointment is in the Department of Electrical Engineering and Computer Science, and he also has appointments by courtesy in the Department of Medical Engineering, Biomedical Engineering, and the Department of Statistics. He received his bachelor's degree summa cum laude from Boston University in 1890, and a PhD degree from Princeton University in 1884, both in electrical engineering. He is a fellow of IEEE. He has served as president of the IEEE Signal Processing Society and as a member of the IEEE Board of Directors. He has received numerous awards for his scientific research and service to the profession, including the IEEE Signal Processing Society Technical Achievement Award in 2014, the 2015 Society Award, which is the highest career award bestowed by the IEEE Signal Processing Society, and the 2020 Fourier Award, which is the IEEE Technical Field Award for Signal Processing. He has also received several Best Paper Awards from various journals and conferences. He has received the University of Michigan Distinguished Faculty Achievement Award, the Stephen Atwood Excellence in Engineering Award, and the Scott Fogler Award for Professional Leadership and Service, all from University of Michigan. Professor Hero's recent research interests are in high-dimensional spatial temporal data, multimodal data integration, statistical signal processing, and machine learning. Of particular interest are applications to social networks, network security and forensics, computer vision, and personalized health. Today, he is going to talk about ultra-sparse models of multi-way data. Please join me in welcoming him.
Thank you, Zoran. I'm glad to be participating in this great idea of yours to try and keep academic scholarly interaction and research vital throughout this difficult time. And I'm really delighted to be able to participate in kicking this off. So I'm going to talk about a set of methods that we've been pursuing over the past 10 or 15 years or so that deal with multi-way data, and in particular, looking at models that have very high scalability with respect to dimensions of data sets that are multi-way, that have multiple dimensions, and that have the properties of being both computationally feasible and also statistically consistent. So let me go the outline here. I'll first just talk a little bit about the general problem of learning multi-way data representations. And learning here just refers to setting up a model and setting up some reasonable way to estimate the parameters of that model. Then we'll go into three different approaches for learning multi-way data representations in the second order as opposed to the first order, which I'll make that clear in a minute. The Kronecker product lasso model, the tensor graphical model, Terra lasso, the Sylvester graphical lasso, and then I'll finish with an application and some conclusion. So these are based on, this talk is based on several publications that by way of showing you these publications, I'm acknowledging my immediate collaborators in this work, Ted Silcardis, who's a former PhD student of mine, now at MIT Lincoln Laboratory, and Christian Greenwald, another PhD student who is now at IBM AI Research, Shuheng Zhao, who is in California at Riverside, University of Riverside professor there, who was key in leading this idea of a tensor graphical lasso, and then Wayne Yu and Byung Zhang, who are both current PhD students. Multi-way data is simply a set of data which can be characterized as multi-indexed tensor or multi-way array, which I call Z here, and we have K different modes or dimensions with index sets I1 through IK, and the dimensions are D1 through DK. And so the total number of elements in this array can be enormous. It's the product of the K dimensions. So that can be in the millions or billions or even larger in some applications. And so one of the challenges is how do we generate models for this type of multi-way data, high dimensional with so many entries, and what the classic approach to doing this is to assume that the data cube has sparsity either in some basis, like a tensor basis, so that you can represent it on a tensor, a set of tensors that can be efficiently computed and separates the problem into subgroups of indices, analysis that is of subgroups of indices, and it may also be sparse in the sense of the natural basis with lots of zeros in that array. So the first order representation has been the mainstay of tensor analysis, multi-way data analysis, and Tammy Kolda and her co-authors have been real pioneers in this area. And basically, first order representations, what I mean is you're interested in learning the mean representation. So if you imagine that this multimodal data cube has some distribution, statistical distribution, you have IID samples of this big array that you're interested in estimating those fixed effects, those mean effects, if you like. And so you try to represent the matrix Z through some outer product of vectors or some Kronecker product of matrices of compatible dimension, or a Kronecker sum of matrices. So first order representations are very effective when your statistical variability of the samples of Z in this IID sampling environment are regular and the mean is stable, right? Second order representations, on the other hand, aim to learn the covariance or inverse covariance matrix of Z, so the dependencies between elements of Z, where the mean has effectively been subtracted or abstracted away, if you like, right? So the covariance or the inverse covariance are defined as the variation mean squared of Z, the elements of Z, about their mean and their covariation over different indices, right? So that's our objective. So we're really interested in second order representation, multi-way data learning, and that is learning the covariance or the inverse covariance, the dependency structure of these multi-indexed arrays. So a couple of examples here. Spatiotemporal data, so k equals 2 in this particular case, if you consider time is one dimension, range is one dimension, and the image that's formed by the pulse radar as another dimension. And so this type of spatiotemporal data is very common in remote sensing that attempts to construct a cube of images, images that are indexed over the range bin that can characterize a particular scene. And so in these types of images, one can look at a slice of this three-way tensor here, and then we can vectorize that slice into n columns by taking successive columns of matrix and stacking them on top of each other, and then you get a vector cross product. And so if you have multiple realizations, that is IID samples of this data cube, then you can compute a covariance by taking the expectation of statistical expectation, or the mean, if you like, sample mean of the realizations times their realizations transpose minus the mean transpose. And so by working with multi-way covariance representations, one can more effectively estimate clutter covariance that will remove the speckle clutter that you see in this image, this reference image at a particular range bin here, and give you what look like continuous trajectories of objects that are moving across range. So the issue is that this is an enormous covariance matrix, right? In the example here, it's 150 by 150 by 400, so a million element, a million by a million, so 10 to the 12th elements of this matrix. And so these multi-way representations are absolutely essential for this type of data. Another example is genome temporal data. So instead of spatial domain, we have the genome domain. And in this particular case, we might have 30,000 genes in the genome by, say, 300 samples. And so again, this is a million by a million covariance if you stack all of these columns together. So you need to have these types of multi-way representations to really get at the covariance in a reasonable fashion. And so this just shows a particular example that came out of this paper that we published a few years ago, where we applied what we called Kronecker product PCA of the covariance matrix, which this just shows the temporal component, which for a cell cycle data set, where you can now clearly see these cell cycle, they're basically 3 cycles of 24 hours for a yeast type of data. So covariance representation, as I just mentioned, is a very high dimensional object for an already high dimensional multi-way array. And so for a two-way D1, D2, we have a D by D covariance matrix, which again corresponds to taking the covariance of the vectorization of this array. And so what you should notice is that, and this is the key to these Kronecker product factorizations and Kronecker sum, is that there's a patterning in this covariance matrix where each one of these blocks corresponds to the covariance matrix in over one dimension, but with the correlation coefficient multiplying that covariance matrix over another dimension if you're using a rank 1 Kronecker covariance estimate, say. And if you're using a higher rank estimate, you still have this patterning that can be taken advantage of. And so that's really the key to being able to approximate covariance matrices or inverse covariances, which have the same patterning, using Kronecker or other types of products. So it's just it shows now the types of penalties other than the L1 norm. So many penalties have been chosen in the literature. I'm just showing a few here. I'm not going to dwell on this because it's not the main point here, but the Gaussian graphical model framework assumes a sparse inverse covariance, a sparse partial correlation matrix, because the graphical model in terms of the covariance matrix or inverse covariance matrix is the graph has dependencies which are given by a graph whose edges correspond to the non-zero elements of the inverse covariance. So I and j nodes in the graph correspond to the variables I and j in this vectorized multi-way array. And if there is non-zero inverse correlation between those, or conditional correlation, conditional covariance, conditional dependency, then there will be an edge in the graph that describes the graphical model. And so one can use various penalties to enforce this type of sparsity to get a Gaussian graphical model. G-lasso or Bayesian sparse covariance estimation. Concord is another method, which I'll be talking about later in the context of Sig-lasso. And then some methods that preceded the method that I'm going to show you for tensor graphical lasso, which are introducing explicitly a product Kronecker or Kronecker sum structure onto the inverse covariance, so sometimes called the precision matrix. So why do we focus on the sparsity and the covariance or the inverse covariance? Well, to make a long story short, you get a graphical model if you incorporate sparsity on the inverse correlation, in the sense that the model can accommodate things like a Markov random field, where you have conditional dependency as opposed to marginal dependency that defines the dependency structure or the independency structure of different indices in your multi-way array. And so usually only one of the sparse correlation, one of the correlation or the inverse correlation are sparse, unless you have a block, a diagonal correlation with lots of small blocks, let's say. And so most of what I'm going to be talking about here on in are for sparse inverse correlation because of this mapping directly to conditional independency. And specifically, I'm going to show that this sparse inverse correlation model is actually a much better match to the physics of ODE or partial differential equation generative models for measurements of physical quantities. Okay, so what is the Kronecker product representation? It's probably the simplest tensor representation one could go with. It assumes that this covariance matrix or inverse covariance is a Kronecker product, is a product of two matrices, maybe a P by P and a Q by Q matrix A and B, where D is equal to P times Q. So P would be D1 and Q would be equal to D2 in this case. And you get this patterning, right, that I was just showing before in the picture of the covariance matrix for the vectorized Kronecker product, A Kronecker B. You have the same matrix, maybe a spatial correlation matrix, but weighted in different locations of this big, large D by D matrix by the corresponding correlations, maybe the temporal correlations, or the correlations between genes that are characterized by A. So it's a very intuitive representation that naturally breaks up the domain contributions to a multi-way dependency. And so there are very nice properties of the Kronecker product that include invariance to positive definiteness. Inverse is very simple, simply computed by taking the inverse of the Kronecker factors. The determinant is the product of determinants and so forth. This is a very useful property that enables us to compute things like Frobenius norm squared for approximation of one matrix D by a Kronecker product by projecting on various, in this case, one-dimensional subspaces in a reshaped domain. I'm not going to talk much more about that, but suffice it to say, Kronecker product have really nice properties. And there's a stochastic representation for a Kronecker product. What do I mean by stochastic representation? Well, we want to be able to interpret the model. And so to interpret the model, a natural interpretation would be that that there is some canonical process, like maybe a Gaussian process with an identity covariance matrix, which is simply passed through a simple sequence of operators to yield the multivariate, multi-way model that has the desired model structure. So if indeed in this case we assume that Z is a random matrix that has a covariance or inverse covariance of this form, then if you define the square root factors of A and B, then this random matrix has a representation in terms of a white noise or IID multi-way matrix that of same dimension as Z. And so that Z therefore has a representation as a filter on the left and a filter on the right applied to a canonical Gaussian isotropically random noise. So this is very useful because it allows us to generate the realizations from the estimated covariance or inverse covariance. And we therefore have interpretation of filtering or operations on rows and columns or multi-modes in a k greater than 2 case. Very important property. So just to show the Kronecker product to model how much it saves, if you take relative to the representation, if you take an 18 by 18 covariance matrix that has a completely unknown cross-correlation parameters, the entries of that matrix, then represent it by the Kronecker product of a 3 by 3 by a 6 and times a 6 by 6, then you have a reduction in number of unknown parameters from 18 times 17 choose over 2 in the one hand versus only 18 parameters if you represent it this way. So there's let me say an economy of scale here by assuming this type of generative model in terms of Kronecker factors. If you incorporate sparsity in addition, then in that case, you can reduce the number of parameters to a fraction of that, right? So to 7 unknown parameters from 153 unknown parameters by inducing sparsity and Kronecker product. So then the question becomes, how do you estimate? How do you infer? How do you extract the best estimates of these Kronecker product factors from a set of IID observations? And so one way to do that is to maximum likelihood or maximum penalized likelihood, where you have sparsity penalties on A and B, the structural Kronecker product conditions are imposed directly, and this then becomes the same likelihood function or log likelihood function, negative log likelihood function with these penalties that we had before, except that the omega is now replaced by A Kronecker B. That's all that's changed. And what you get from this by doing this optimization now of optimizing this over A and B, this is not convex, so alternating maximization or minimization here can be employed but may not be guaranteed to converge. But you get these transposed regularized covariance algorithms or KG-Lasso algorithms that can be characterized if they converge to the right limit. So parallel lasso is a different approach. Instead of looking at a Kronecker product, we look at a Kronecker sum representation, and that gives you a double economy of scale, if you like. So a Kronecker sum representation for the inverse covariance, A Kronecker sum B, is simply the sum of the Kronecker products of A and I and B, where I here has the corresponding compatible dimensions, so Q and P respectively. So this you can imagine is probably going to simplify things, because you now have a linear dependency. If you fix B or you fix A, you have a linear dependency in the Kronecker product representation of omega, right? The inverse covariance. But now this is a now a convex function, a linear function of A and B globally, right? Because of the fact that we've separated A and B out this way. So the tensor graphical lasso is a generalization of the bigraphical lasso that my colleague Shuang Zhao and her student Kalitzis derived, and I'm going to now describe how this works. So we have a Kronecker sum property that several properties that we're going to have to exploit. Unfortunately, these properties are not nearly as nice as the Kronecker product properties. So you do have associativity, you have linearity, as I just mentioned. This is for a threefold, three-way Kronecker representation. You have a distributed rule, which is a little bit strange. And there's no simple eigendecomposition property, unlike the Kronecker product. But you do have some representation of singular value decompositions of Kronecker sums. And give you an idea of some of the differences between the Kronecker sum and the Kronecker product, I give you this example. So this is a graphical model of a three-way Kronecker representation of a matrix, let's say a covariance or an inverse covariance matrix. So again, there's four variables here. Each variable along each one of the modes, right? So mode 1 has 4 variables, mode 2 4 variables, and mode 3 has 2 variables. An edge exists if there's correlation between those variables, and otherwise there is no edge. And so you can represent these as graphs in each mode. And if you then represent the overall inverse covariance through a Kronecker product of these 3 graphs, which is called the product graph, then you get a set of edges, which I show here, rooted. These edges are rooted at this particular node in the covariance matrix. If you use the Kronecker sum with the same graph, you get the set of edges that are indicated here. So the Kronecker sum, this is what's called a Cartesian graph as opposed to a product graph. And the Cartesian graph, you note, has many fewer edges. So this is due simply to the fact that in the Kronecker product graph, you are, if you like, amplifying each one of these graphs by a product of all the others, right? Whereas here, it's just a sum, so you don't get that amplification factor of the number of edges. So this is going to translate into sparser models and faster algorithms for estimating the model. And so this is the algorithm that we proposed, the Terra Lasso, for now optimizing this now penalized, whereas there's the penalty negative log likelihood, where again there's the inverse covariance supported on the positive cone of dimension P. And actually that's dimension D, should be D here. And then we have a penalty which penalizes the off-diagonal components in the successive Kronecker factors in the Kronecker sum. And this MK is the codimension of dimension K. In other words, it's the product of all the other dimensions except for the dimension K. And then rho K is the parameter that you use in order to regulate the amount of sparsity you want in this Terra Lasso representation. So yeah, there's MK right there. And so now you form this covariance estimate. Actually, I haven't subtracted the mean here. Normally you would subtract the sample mean. And we implement a first order fast iterative thresholding algorithm, a Beck and Tiboul type of algorithm for this, and we call it the tensor graph ISTA. So FISTA is Beck and Tiboul's algorithm for optimizing objective functions such as this, which is this objective function is convex, and so you're guaranteed to have a unique maximum as long as n is sufficiently large. And so then we have a theorem that tells you basically how to choose these regularization parameters, or OK, right? So the theorem basically says that if you want to minimize your Frobenius norm error between the estimated inverse covariance and the true inverse covariance under this Terra Lasso model, then if you choose rho K like this, which is inversely proportional to the codimension of the kth mode in the multi-way array. Then you get this this bound, and the important thing to note is this bound is very comparable to the bound on the convergence, statistical convergence. This is right. So this is a probabilistic statement here with probability at least very close to 1. This is going to be less than this bound, which can become arbitrarily small as you increase the number of samples, or as you increase the number of codimension, or as you increase the number of dimensions, I should say, in such a way that the minimum codimension is increasing. So as compared to the G-lasso, the Terra lasso statistical convergence rate, which is what this rate is here on the right, is faster by this factor of the codimension, which can be enormous, right, in cases where you have lots of dimensions. And just as a numerical illustration of this, these are runtime complexity comparisons comparing to the big lasso collections. That was a proposed method for estimating Kronecker sum representations for k equals 2 two-way arrays versus the Terra lasso with runtime indicated here. Due to the fact that we're using this FISTA type of optimization, and that we have this projection interpretation of the in order to of products in order to compute the Frobenius norm and the trace in particular of the product of the sample covariance and the inverse covariance that we're trying to estimate, we can allow the number of in the multi-way, the number of modes to get larger. Here we have 5 modes, dimensions, DK or 65, the number of elements is on the order of billions, and we get a runtime on the order of 120 seconds or so, right? So there's a speed up by 2 to 4 orders of magnitude, and as compared to ordinary G-lasso, which scales in terms of the complexity per iteration as the product of the dimensions. Here, computation scales only as the sum of those dimensions. So again, very, very significant speed up. Just to show a kind of fun application where we're looking at sort of weather applications. So here we have the National Center for Environmental Prediction data, where we look at a Western grid, 10 by 20, and an Eastern grid, and we're going to compute the Terra lasso estimates of the Kronecker sum representation for those 2 covariances, and I'll show you now what we obtain. So here we can separate. This is only the spatial factors. I'm not showing the temporal factors here. This is these factors on the Eastern grid and the Western grid. You can see that the sort of interesting and in hindsight obvious fact that the dependency structure in terms of spatial influence of one, in this case, wind velocity cell on another wind velocity cell in this NCEP data set, that dependency breaks at some point in the longitudinal domain, and where that breaks is precisely at the Rocky Mountains. So this sort of recapitulates what probably is pretty obvious to meteorologists, that there are really 2 different types of weather systems on the average between the western and eastern parts of the U.S., and that the dependency structure is high in the east and in the west, but there's this sort of break in dependency that occurs at this boundary. These comparisons just show different the covariance components for the in this case it's for the I think it's the latitudinal component of the covariance, and this is for n equals 1 sample. So we're just looking at a single sample because there's so much redundancy in this Kronecker sum representation of the covariance. With 1 sample, we can do as good a job at estimating the spatial covariance structure as we could with 50 samples of the shrinkage estimate. You can see the structure is very similar in both cases, whereas the shrinkage estimates or the Kronecker sum estimates or product estimates have lots of artifacts when you're using a single sample to estimate the structure of these covariances. That's just the longitudinal component, I guess. And then we can apply this to validate that the model is reasonable to predicting the season given a data sample. And so this just shows a low S fit to the average of the wind speeds at different days of the year, showing that there's some variation. The summer is here, the winter's fall are on the other side, and so this just shows. I'll just focus on this picture here that using this Kronecker sum Terra lasso with only 5 of the. I don't restart. That's for sure. Sorry about that. We get an error rate which is significantly lower than, say, the Kronecker product model using Kronecker G lasso. Right. So I'm going to finish up now in the 7 minutes I have left with the latest, let me say, variation on this theme of modeling dependency in multi-way data and estimating that dependency with sparse structured models with a model which we have called the Sylvester graphical lasso. The motivation for this model is that the Terra lasso, that is the Kronecker sum model for the inverse covariance, is not a simple generative model. There is no simple interpretation for for a process that has a Kronecker sum inverse covariance in terms of simple operations on an IID, white noise, Gaussian matrix by the Kronecker sum factors. So with SIG lasso, we have such a representation. We have a generative representation, very simple representation. I'm going to motivate that by looking at physical processes and modeling physical processes through their second order covariance or inverse covariance. So let's assume that we have some continuous state physical process with a differential operator D operating on the observed process U, and F is some driving source, noise, or driving conditions. This classic assumption that we have some domain omega, we have a boundary of the domain gamma where U is equal to 0, so the measurements are equal to 0 on the boundary. And so now we have a classic partial differential equation with boundary conditions and a differential form D. F is a generating process, as I said. It could be any differential operator, like an Euler-Lagrange or a Laplacian, or we're going to look at elliptical Poisson equation operators in a minute. And then the PU equals F can be looked at as a generative model, right? You basically put in an F, which might be a Wiener process, like a white Gaussian noise, let's say. And then this describes the observations U as a result of applying this simple differential operator. We want the same type of generative model for the inverse covariance. And that's what we're going to be able to do with the SIG lasso type of approach. So there are lots of numerical solvers that it could be implemented here, like finite difference methods, Euler differencing, finite element methods. And so if you discretize this, you get of course, a matrix differential operator representation applied to the observation U driven by some B. Okay, so This gives us equivalence between a differential form for a continuous domain omega differential equation as according to an Euler discretization, for example, that gives you du equals b. And so lots of different ways of discretizing are available that aren't really show that as a reference. But the properties of D are very important. And this discretized operator is sparse because the partial differential equation only has local data passage property, right? Because of the differential equation, only the nearest neighbors of one particular node, let's say this one there, are going to influence the evolution of that equation as you say iteratively solve using a finite element method, this PDE. It turns out that under the Euler discretization that D has Kronecker sum structure. Interesting. And that then leads directly to a representation that if we model the B as this white noise, independent noise, that has some maybe variance sigma squared and identity covariance, then the inverse covariance has a sparse square root factor, which involves this D, Kronecker sum. So let's just look at an example to illustrate this. Let's assume we have 2 dimensions. So omega is a 2-dimensional domain. And let's just look at the Poisson equation. So there's the Laplace operator. And if we discretize that with the simple Euler scheme to an n by n grid, then if you move things around, you can represent U at a node ij in terms of the nearest neighbors summed in a particular form of U at nodes next to it, right? With some factors, and then F is of course also discretized here. And now this can be converted into a matrix equation on the vectorization of this multi-way array U. And so if you define the discrete Laplacian, then you have this Kronecker sum structure B, Kronecker sum B U equals B, describes the Poisson equation in its discrete domain. So then the covariance, the inverse covariance, is simply the product of the Kronecker sums and the Kronecker sum transpose. And so this now gives us a generative model, because we can now, as I just mentioned, assume that that the observations which we've been calling Z in the past obey an equation which has this Sylvester structure, which I show here, because of the Kronecker sum structure of that matrix B. Now, this is actually not the same B as the previous slide. So this is in the so if you have if you want a Kronecker sum covariance, then that has A and B as Kronecker sum factors, then under this this Sylvester model, the Z, the multi-way array, satisfies this generative equation that says that you have a white noise W, and Z is the result of applying A to the left and B to the right of Z and then adding them together. That's the Sylvester equation. That's why we call this the Sylvester lasso or Sylvester G lasso. This is equivalent if you vectorize Z by concatenation of its columns to the Kronecker sum A, Kronecker B. All right, so that gives us this stochastic representation I was just mentioning, and it also gives us an inverse covariance, which is the square, because A and B are symmetric matrices by assumption at positive definite. It's the square of this Kronecker sum. And of course, in a k way, you'll have a kth, the square of a kth order Kronecker sum. And so we define our estimator by using an analogy to the Concord method that was introduced by Kare O and Rajaratnam in 2013, which is basically a node-driven what's called a pseudo-likelihood approximation to the likelihood equation. And so I'm not going to go into that for lack of time, but you can see the paper if you're interested. The SIG-lasso is a convex optimization. It has a penalty where the penalty coefficients are lambda k. And we use a cyclic coordinate descent on to solve this, all which effectively gives us a convergent algorithm because of convexity, strict convexity under conditions on the number of samples. So we solve this. This just shows, I'm not going to bother dwelling on this because I'm already out of time, but the theorem that is analogous to the theorem for Terra-Lasso tells us how, first of all, how to choose these regularization parameters to get a convergent sequence that is consistent in terms of estimation consistency. Here, beta are the off-diagonal components of the inverse covariance. We also get sign consistency, so we can estimate the signs with probability 1, with probability 1 minus this accurately. This just is an example, which I won't dwell on, that illustrates that the Kronecker product and the Kronecker sum are kind of combined in the SIG-lasso, because the SIG-lasso inverse covariance matrix is the square of the Kronecker sum, which can be represented in terms of Kronecker sums and Kronecker product. So you have a compromise between sort of the sparsity and the Kronecker sum and the representation generative model of the Kronecker product. And this just shows that SIG-lasso, Kronecker sum, and Kronecker product that the SIG-lasso is robust, if you like, to changes in the assumed structure. If it's actually not, if the omega is actually a Kronecker sum and not a square of a Kronecker sum, you don't do too badly in terms of for the right choice of regularization parameter compared to the matched Kronecker sum Terra-Lasso estimate in terms of the MCC, the Matthews correlation coefficient between factors. And I'm going to skip this example because I'm going to want to leave some time for questions. But this example, you can go to the paper. It's applied to an alcoholism study for a graphical model that's pulled out of EEG from an alcoholic subject and a non-alcoholic subject over several time points. And we can apply the SIG-lasso to this and obtain results which can have interpretations which I'm not going to go into. Okay, so just as a conclusion, we have presented various types of multi-way tensor representations, Kronecker representations for the inverse covariance of multi-way data. And these three different methods all have their niche. The one that's the most scalable is the Terra-Lasso. The one that has the ones that have generative models are the K-lasso and the Psi-G-lasso. And the Psi-G-lasso is the only one that's directly related to the solution of partial differential equations, which means that, at least from a philosophical point of view, that the SIG-lasso is a sensible type of model if you're dealing with processes that you believe have sort of physical generative origins. So thank you for listening, and I'm happy to answer any questions.
Thank you, Professor Hero, for the wonderful talk. Maybe let's look at some of the questions raised in the Q&A section.
Yes.
So the first question is about explaining the slide. So Patel asks on slide 15, are the matrices A and B tridiagonal matrices? The matrix A and B.
On slide 15?
Yes, on slide 15.
This one? No, I'm sorry.
No, I think, so the question says slide 15.
Yeah.
I think it's from the beginning.
Right. Yeah, well, this is slide 15. So, so in this case, these are tridiagonal matrices. The generating matrices are. Of course, the Kronecker product is not, because the Kronecker product has this superdiagonal structure. Right? And that's one of the advantages of these Kronecker product representations, is you can start from relatively simple, like tridiagonal representations, and end up with richer structure by layering on different Kronecker product, Kronecker sum representations.
Thank you very much. So another question is regarding the optimization. So in terms of solving those regularized solutions, is it possible to ensure, although they are convex, how to ensure that the iterates always lie in the constraint set, such as it can be factorized using Kronecker sum?
Yeah, that's a great question. Now, some of those constraints are baked in, right? So in the case of the Kronecker sum, like the one I'm showing here, we have a positive cone, which is the positive cone constraint, which we enforce by simply using a projected gradient approach, right? So since this is a convex objective, the projected gradient will still converge. We, of course, the asymptotic convergence rates don't depend on those projections as long as you're in an interior point. Solution is interior to the cone, or is interior to the structure that you've imposed. But of course, at finite iterations, that projection may have the effect of slowing things down in terms of runtime. But for the Kronecker sum representation, you can see that the Kronecker sum structure is actually baked into the objective function. So there's no necessity to take any additional constraints into consideration, because you're estimating separately these psi k components, and then the sum of those psi k's gives you your inverse covariance estimate. Of course, as long as you project onto that positive cone.
Okay, thank you very much. So another question is would the Sig lasso be particularly well suited for the analysis? Would the Sig lasso be particularly well suited to analyze the multivariate time series where the underlying process is a solution of the ODEs rather than PDEs?
Yes, yeah. So this characterization that I'm showing you here, that if you discretized Euler discretization will apply regardless of whether the domain indices come from space or space and time or space and wavelength or what have you, right? So we haven't applied these to time series, but that's a very interesting idea, that if your time series can actually be modeled as a differential equation of this type, then clearly we could do so. I must caution, though, that in time series, often there are long-term dependencies, right? And so long-term dependencies can't be adequately modeled with a simple ODE, right? So one can model them by, for example, looking at a fractional ODE, simple ODEs do not necessarily give good results when there might be long-term dependency. So, for example, stock market or other types of time series that don't have this local data passage type of property.
So a further question regarding this problem is that is the boundary condition explicitly taken into consideration of your algorithm?
Yes. So no, it's not. We could, if we so desired, do a reparameterization, because here, of course, the domain here is not necessarily Cartesian, right? So if you can't find a change of coordinates which convert this domain into a matrix, right? Then of course you have to make some adjustments. For example, zero padding, and then you would run into the issue of having to enforce zeros outside of the domain, right? But in the examples we've looked at, the domain has always been a square domain, if you like, or cubic domain, where all of the variables are independent variables, right? You can index the domain independently along each axis. But of course, you know, the general theory of PDEs or ODEs allows a any smooth domain to be accommodated in a solution. Of course, those enforcing those boundary conditions is also a problem that's received lots of attention in the numerical PDE solving literature, right?
Okay.
But we have not run into an application where we wanted to impose that. If we do, then you know, I think that, you know, zero padding is the obvious way to go about it. Just find the largest, the smallest Cartesian cube that contains the domain, and then solve the equation in that domain, the generative model in that domain with zero padding.
Oh, okay, thank you. So another question is raised by an anonymous attendee that how can we know that the Sylvester's equation has a solution in the application of a stochastic representation? Is it possible that one of the matrices be rank deficient?
Yeah, so, right. And so indeed, there may be, in the generative model, there could be a, so just pointing here, it could actually be that in the solution that A and B are not individually full rank, right? They may be rank deficient, but the solution, since we're always projecting into the interior of the cone, we enforce using the regularization property of the regularizer lambda, that their sum be positive definite, right? So that means, you're right, there may not actually be a unique solution to Z, but effectively we're not interested in this second order modeling. We're not necessarily interested in recovering the generative model per se. We're interested in recovering the dependency structure. So again, the second order multi-way dependency is what is of primary interest. And so we may not have identifiability of A and B individually, is my point, right? But there is identifiability of omega.
Mm-hmm. Okay. Thank you. Another question is raised by two attendees. Is it possible in practice, how if we have a multi-way tensor data, how to decide which kind of covariance structure to use in practice?
Yeah, no, that's a great question. a lot of it is predicated on computation, of course. I mean, that's the easy way out. You just can't implement a unstructured covariance estimate, even like L1 G-lasso, if you have billions of variables, or even tens of thousands, unless you have extreme sparsity in your model. So computation is usually expedient. In terms of the choice of the model, if you have some information about the generating source of your data, then of course that can guide you in choosing a particular approach, right? So if you know that the Kronecker product structure is a structure that really matches directly the problem at hand, and so for spatial temporal time series is a good example of that. Say you have a multi-dimensional time series, and each dimension is some linear combination of a single time series. I should say each multiple time series is a combination of the time series that are nearest neighbors to it. Well, it turns out that a Kronecker product model is actually a good model for that. If you have that kind of locality, where you can organize your time series into some structure where you can impose that type of nearest neighbor locality, which corresponds to a kind of tri-diagonal, in the case of a one-dimensional ordering of the time series dimensions, a tri-diagonal type of structure in the Kronecker product. It's not a probably not surprising that there is no universally best approach. Again, one is guided by both computation, which implies things like convexity of the resultant objective function, so that you're at least getting you're getting close to an optimum solution, and then of course one can also use, if you're interested in going beyond a simple Kronecker sum or Kronecker product, you can use the classical result that any covariance matrix can be approximated by a sufficiently large number of Kronecker product components. And so there you can go after a Kronecker product decomposition of the inverse covariance, which is something that we're working on right now, which would be a more of a universal approximation, if you like, as opposed to imposing some particular structure.
Mm-hmm. Thank you. Maybe due to the time constraint, maybe let's have our last question. So Feng Liu asks that could you please elaborate more on the details of the application on EEG data to infer the brain networks? So in this case, why do we need the Kronecker Kronecker sum? Sorry.
Right. Yeah. Okay. So in this problem, we generated a solution, as I'm showing here, which sort of implicitly, in terms of the Kronecker sum representation, assumes that there is some physical underlying model for the EEG array measurements over time, right? And so one can certainly go to the fundamental theory of compound action potentials and Euler-Reuter equations in computational and systems biology to motivate a sort of a PDE type of model that might underlie this array of electrodes that are co-located on the surface of a scalp of a subject, right? And so the motivation is really through a sort of a philosophical argument that we know this data is coming from a human subject. We know that the mechanisms that generate the compound action potentials obeys certain equations that can be characterized as differential equations, and so therefore a sig lasso seems like a reasonable approach to apply.
Okay,
and indeed,
thank you very much, Professor.
Yeah, indeed, we get similar results as other analyses of the same data, except with higher scalability and interpretability.
Okay, thank you very much. Maybe let's just finish here, and please join me in thanking Professor Hiro again. Thank you very much.
You're very welcome. It was a pleasure to speak to you, and I look forward to the sequence of very exciting talks to come.
Thank you. We are looking forward to it as well.
Thanks, Aaron and Nathan.
Thank
so
you.
long, everybody.
Also, thanks everyone for joining. We are looking forward to seeing you next week. Please feel free to contact the seminar organizers, and if you have any questions or suggestions. So see you next week.
Yeah, later we will post the recording of this talk to our website, and I will send out an email.
Cool. Okay, great.
Okay.
Good.
Okay.
Thank you. Thank you for organizing it.
Thank you. Bye.
Thank you.
Bye.
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 Bye.